Gannison, where are you that I don't hear the streets of India? How did you manage that?
Yeah. So, before starting, Robert, actually, I just want to introduce, the panelists also. There are a bunch of panelists are here to, support this webinar. I have, Sameer Shande from University of Oregon. He has been collaborating with us for last 2 years, and and contributing many things. And then I have Abhinandan from NIE, National Institute of Engineers, and also I have, yeah, Abhinandan is also a great collaborator with the Power9 system, and I have IIT Bombay professor by name Nataraj, PSV Nataraj, and he has got the Open Power Center of Excellence, since 2016. He has been running that, and I welcome all panelists also to be part of this, 2-hour session. Thank you. Please go ahead.
Yeah. Okay. Well, just to start with, I hope maybe next year we could meet in person at maybe supercomputing or the ISC version. It's a lot more fun to actually shake hands than fist bump through the computer, but here we are. So today I'm going to talk about kind of my passion, which is working with new users and helping them or transition them from new to intermediate and hopefully power. And of course, we're going to talk about this in relation to the IBM Power system. So everything that you're seeing here will ultimately facilitate our users on Power. So as Gannison said, I am at Virginia Tech. Virginia Tech is in the ACC. So in a normal year, this is kind of what I'd be gearing up to do. Think about basketball. And, in spite of me being a UVA fan, which I'll talk about in just a second, my son is more of a Duke fan. And of course, you can't talk about ACC without Michael Jordan and UNC, but this isn't a normal year and we do what we have to do. So who am I? Again, my name is, I go by Bob Settlage. I'm a researcher, I'm a collaborator, I'm an educator. I work at Virginia Tech. Virginia Tech is a tier 1 research institution, but I'm a UVA grad. So I am a chemist by training. I also now have a statistics degree from Virginia Tech. So I have this split personality, I guess. I'm a computational scientist within advanced research computing, which I'll talk about here in a second. So, who am I really? Well, I'm a Virginia Tech computational scientist. It happens that Virginia Tech is an institution that feeds their students well, and I can attest to the food here is really nice. But we have a few things that we're maybe noted for that no other college can claim. So we are the only school to hit the trifecta of sequencing and assembling the transcriptome and transcriptome of our mascot. Our mascot is the turkey or the Hokie bird. We also, in the fall, serve our mascot up on Saturdays. So if you run around the football stadium here on Saturdays, you'll see these booths serving smoked turkey legs, which are fantastic. And then we also save our mascot in November. So there's a tradition in the US. We'll see if President Trump does it this year, but we pardon a few turkeys on from the annual feast. And we house them here at Virginia Tech. So I think currently we have 2 turkeys named something like, drumstick and potatoes or something like that. So, all kidding aside, this is a pretty important project because turkeys happen to be a pretty important food source in the US. It's kind of third in terms of meat production. And I happen to be involved in that project, so kind of cool. So what are we going to talk about today? I'm going to introduce my group, so Advanced Research Computing here at Virginia Tech. And then we're going to start talking about users and how we enable users here at Virginia Tech. So specifically, we're going to talk about something called Open OnDemand that I'm involved with here at Virginia Tech. And then kind of our work in progress is enabling users to reach a different level of sophistication, and I'll introduce that towards the end. Okay, so advanced research computing, what is that? Well, we're one of kind of many across the United States. Basically, as I describe it, we are the scientific base that sits in front of the clusters here at Virginia Tech. So we're a unit within the Office of IT at Virginia Tech. So we're sit in central IT that has some ramifications that I'm not going to talk about today, but that's kind of where we sit. Our goal is to provide centralized resources for research computing and visualization. So not only do we have a lot of high performance computing resources, but we also have visualization resources for those who need something more than what you can do on a local compute platform. So for instance, we have a big 3D visionarium where you can totally immerse yourself in your data, which is pretty cool. It also includes a sound component. So not only is it visual, but it's also audio, which is not totally unique, but it is certainly not mainstream. And then, of course, we have a staff of computational scientists, which is what I am, and system administrators, and GRAs and other people to help users really get access to and then use computational resources within Virginia Tech. So that was kind of talked through, but in words on this slide. Again, our goal is really to help users both access and then use resources for research at Virginia Tech. So I say research, but I mean education. So in my view, we're enabling a spectrum of users, and we really start at the education side, and we hopefully transition users who have need to become what I hope are computational scientists. So as a tier 1 research institution, students are really our research powerhouse. And as I say it tongue in cheek here, it's kind of true. Our students hit our clusters, and they do some things that really surprise us every day. And we have to both facilitate that, but we also have to protect against it, and then we also have to enable it. So as I like to say, the best researcher is one who tries random things, but also takes notes about what they did, so that when something stupendous happens, they can repeat it and bring us to somewhere new that we haven't been before. And sometimes that's really just a random click that fortuitously led to something interesting. So here's kind of my view of a user. So at one end of the spectrum, we're all beginners, and we become HPC users through need. So suddenly we're presented with more data than we knew how to use, for instance, and that's kind of how I became a new user. And then we were given access, and hopefully we had training. Sometimes our training is all on the web, Google or whatever. And there's kind of good and bad moments in that. We've all maybe experienced the RM minus RF star. It's like, oh shoot, what did I just do? But we exit that stage as a new, better user, and hopefully we enter the stage that I'll call intermediate. Maybe we were facilitated to enter this stage through having deadline, so we were forced into upping our game. Maybe through curiosity, maybe through monitoring, we enter a new phase in our user life cycle. Maybe then a few users kind of enter this power stage. And so they up their game to include automation. Maybe they introduce to themselves pipelines. Maybe they also have alerting as a part of their compute. So the computer tells them when they need to do something. Kind of cool stuff. What we're going to do is we're going to facilitate this transition. So that's really the goal of the computational scientists within ARC at Virginia Tech, is to enable new users, but then rapidly facilitate their use and their progression into, say, intermediate users. And hopefully some, again, continue that progression and become power users. The way we're going to do this is we're going to use a suite of open source products that I've listed here on the bottom: ColdFront, Open OnDemand, and XDMoD. And we're going to basically expose users to these products to help facilitate their progression. So the first one, ColdFront, I'm not going to spend a lot of time on today, but really ColdFront is about user management. And so it's how we onboard our users. It's how we allow our principal investigators to manage their groups. It's how we, within ARC, kind of offload some of the mundane sysadmin-y type stuff, forming groups, adding users to groups, all that kind of stuff, to the PI, so we don't have to spend a lot of time there. We will use Open OnDemand to facilitate cluster access and lead users along this user spectrum, and we'll talk more about that as we go forward. XDMoD is more about job performance metrics, and I'll show a little bit more about that towards the end, but XDMoD is where users can really see the ramifications of their code. So they'll be able to see, for instance, that their GPU utilization is low, and maybe they can do something different. And so what I like to say is this is kind of a gentle introduction to HPC, and it really speeds progression of user from new to intermediate and hopefully to power. Okay, so yes.
Can you change your the screen view? Actually, you know, we like to see the bigger picture. You know, just one slide.
Oh, sorry.
Yeah, looks like.
You're seeing presenter view.
Yeah.
Darn it.
Yeah. Okay. I think.
Let me get it full screen.
Full screen, yeah.
Oh. My Zoom controls are sitting over my my controls. Just get rid of some stuff here.
Yeah, I think this will do actually. If you have some inconvenience, yeah, sure.
Okay, sorry. So now we can both see what's up next, I guess.
There's a suggestion
okay, so,
to click on.
You know, again, this is how I think of users, and what we're doing is we're facilitating their progression. And so, you know, just to start with, the user has to gain access to our clusters. How do you get started on ARC? Well, basically you need an account. You know, a way to log in, and then an allocation. So at Virginia Tech, our resources are free to users. However, we do track usage so that we can kind of get an estimate on ROI, if you will, to use the business term. How do we do that? Well, again, ColdFront. Okay, so ColdFront is where we create projects, we create allocations, and then we assign users to the different projects and allocations. And then in OnDemand, we can then gain access, and I'll show you that here. So Open OnDemand is really a web-based or browser-based HPC access that is fully customizable to the site. Okay, so for instance, here's 3 different dashboards, if you will, on-demand dashboards. One is from Ohio Supercomputing Center, the middle one is from Virginia Tech, and then off to the right, we have the University of Buffalo version. And so what you can see here is that, as an HPC center, we might want to do things like give messages of the day, show cluster utilization, or maybe show some job statistics, something like that. And we can do all that. It's customizable by the site. As I mentioned, what we are trying to do is really facilitate and speed the progression of a user from new to intermediate and then hopefully advanced. We can actually quantitate what Open OnDemand does in terms of this facilitation. So for instance, Ohio Supercomputing Center kind of was able to, through some log analysis, show that users coming in through Open OnDemand had about a 6-minute time between their first login and first job, whereas it was about a day through traditional methods. So people who just SSH'd in, for instance. What that really means or translates to is competitive advantage. And so, even in a company, I think this is something that's important, because not all hires will be hired for their HPC prowess, but maybe they'll be hired for domain expertise that then have need. Okay. So, I think this is kind of a clear indication that we are doing what we are saying we are doing, and that we are speeding the progression from new to user. What all does Open OnDemand provide? Well, really 3 things. The first is file management. So again, browser-based file management. You can see here, I am showing that through the web, I can see my files and directories on the cluster. And I can drag and drop, edit, delete, all kinds of good stuff just straight from the browser. That doesn't seem like a big deal for those of us that are used to being on the command line, but for a lot of users, this in and of itself is a huge benefit. SSH access. So, we're going to talk about GUIs, but not all users want to use this. What's interesting is when you log into Open OnDemand via the web, Open OnDemand now knows who you are, so we can provide you with SSH access through a web-based terminal. Open OnDemand knows who you are, so identity is already determined, and you don't have to two-factor in, for instance, here at Tech. So what that means is for people that maybe have access issues by they're slow typers or something like that, we can get them in a different modality that maybe is enabling. So that's kind of cool. It also means that if people want to use SSH modes of cluster access, they can. So again, it's enabling, it's not detracting. Beyond that, what Open OnDemand is provides is the ability to access lots of different interactive apps. So, I'm showing a bunch here. Jupyter Notebooks is certainly one that is very popular, but QGIS software, RStudio, Stata, Visit, all types of different interactive apps. What this allows us is to do is work through the different issues that a user might have in doing this through the command line. So the reverse proxy and all that kind of stuff is still happening. It's just hidden from the user, and we enable it through the web. We can do more cool stuff that might be interesting to, say, sysadmins. We can, for instance, as I'm showing down here in the bottom right, we can allow users to to give a view-only shareable link. So for instance, in this case, it's MATLAB. Maybe a user is having a MATLAB job problem, and they can provide in a help ticket a shareable link. Kind of cool. So, you know, we can do a lot of cool stuff that not only enable users, but also facilitate support. Beyond that, this really is interacting with schedulers in a different way, but we can script that and we can do other cool stuff. So for instance, what I'm showing here is we can allow users to basically just do a singularity poll. So convert Docker images into singularity images through creation of a job that's kind of hidden from the user, but still gets the job done, and basically just speeds the process up. Traditional scripted workflows are still the workhorse of HPC. What we can do is facilitate how that is done on our clusters. So for instance, we have something called a job composer, which is really just a web-based GUI to create scripts and submit scripts. So our mentality is that, you know, new users have to get on, they have to start to see the cluster. Once that sort of luster is gone, hopefully they can then start to, as need arises, start to script. And so we're facilitating scripting through the web in this way. So in other words, on the far right in that panel is a job script, and we're basically just enabling people to edit that in a more familiar environment instead of going to the command line, for instance, and learning Vim or one of the other command line text editors. So what we're envisioning is this is through a progression and a facilitated progression from, you know, GUI work to get jobs that might be prototypes into scripting, and then hopefully at some point they sort of get to here. So what we're doing right now is we're integrating something called XDMoD. So this is a open source project that has come out of the University of Buffalo. But basically, this is a job log analysis tool that analyzes how a job has used the resources within the cluster. So what we envision is that users will get kind of a user report, as I'm showing on the right here. And we're kind of judging the efficiency of jobs. So we're giving people's jobs ratings, if you will. So, you know, how well did you utilize all the cores within your job? How well did you use the memory? How well did you use the GPUs, for instance? So through exposure, we hope that users will kind of start to ask questions. So through curiosity, engage the computational scientists within ARC. You know, hey, this thing's coming back and saying, you know, 57% of my jobs were inefficient in the core hour reports. What am I doing wrong? And then we can sit down and start to have a conversation about their code and think about what we might do better with them. Just diving into this a little bit more, we are exposing to them the whole XDMoD interface, which is pretty information rich. And we're starting at the very start, which is, you know, how does your job look from maybe a core memory GPU perspective, but then we can start to dive into it a lot deeper, as I'm kind of showing here. The two plots are GPU and CPU utilization. So you can see in this particular case in the upper right that their CPU, and actually this is mine, my CPU use went up to about 69% and kind of hung out there. This was really a job dominated by matrix multiply. At the same time that was happening, my GPU utilization was kind of tapering off. And so now I have a starting point to go and look at, well, what was really going on as I was swapping between these two states. And I can start to ask that next question. Open OnDemand on our systems is available to all of our clusters. So that includes a PowerAI cluster. So we have a Power8 cluster with the PowerAI suite of tools on it. And I'm kind of highlighting that down here. It's called Huckleberry. It's kind of a modest size, but very powerful 14 node cluster. This was a joint purchase between ARC and our electrical and computer engineering department as a recruitment tool. So a lot of people were asking, have you invested in power? And the answer until this Huckleberry cluster was no, and that was a deterrent to people coming to ECE. It's also a teaching tool, so we're using this in both curriculum, but also in things like hackathons and other sort of fun events that we're sponsoring with IBM. It's an AI workhorse. You can see here. So this is kind of the utilization. What was it yesterday at 11:20 in the morning? There was every single GPU was either available or reserved. And so there was no resources available. So our queue was becoming a little bit clogged at that point, but this is a normal state for that cluster. It's very heavily utilized. So how have we enabled users on this cluster? Well, everything on the Power cluster is about the PowerAI suite of tools. So what we've done is we've created a special Jupyter notebook where we can specify the Conda environment. So we're using the IBM supplied PowerAI Conda environment to export basically the deep learning tools. So people can go to Open OnDemand, they can start this Jupyter notebook, and automatically this Conda environment will load, and then people can, in the normal fashion, use Jupyter plus deep learning tools that are accelerated for the Power architecture. This is not a either or scenario, so note that you can SSH into this cluster in a traditional way, load Anaconda as a module, and then Conda activate the Power suite of tools. So both modes work. This is really just an overlay to facilitate access. One question that we had as a stumbling block really for a lot of users, well, great, I can get my Jupyter notebook up, but how do I get access to something cool like TensorBoard to help me with network troubleshooting or looking at maybe real-time how my training is progressing. And so we can also create an Open OnDemand app that will basically just start up a TensorBoard and allow the user to see their real-time training results. And that's what I'm showing here. So what do we do on our PowerAI cluster? I kind of alluded to it in a few minutes ago, but really what we're doing is all types of stuff around educating users and research. And I'll show a slide about that here in a second. One thing that we've done a lot with IBM is hackathons. So we've hosted a couple of hackathons around artificial intelligence or deep learning. And what we're using Open OnDemand for is really moving the focus of the hackathon from access issues to the topic of the hackathon. So when we do it in this way, pretty much immediately we start to talk about deep learning, AI, machine learning, rather than how do I use power, which is really kind of a neat way to do this because we spend more time talking about the science really. In our classrooms, when we use Open OnDemand on top of Power, we avoid the question that really kills the discussion in the classroom for 1 to 2 days, usually, on how do I SSH to Huckleberry in this case. So that's kind of nice. So what we are doing is freeing our instructors from access discussions to allow them to focus really on Power discussions. So what type of projects are we seeing on Huckleberry? Well, again, we're a tier 1 research organization. And so we see all types of different projects. Here's a few. The ones that we see the most of are really around robot coordination and navigation. So those consume a lot of our core hours. We have a lot of people that are very interested in sort of smart city research. So looking at communications and security issues, that's pretty interesting. On the life sciences side, we see some computer vision projects that are looking at crop identification from satellite images and identification of management issues in those crops. So where might I deploy some drones that might be harvest drones, or where do I need water, or other nutrient deployments. There's a lot of work around physics-informed predictive turbulence. So Virginia Tech is an engineering university first. So we have a lot of engineering applications, design of airfoils, or robotics, or computational fluid dynamics, that type of thing. We have a pretty strong presence in prosthetics. So we're seeing a lot of AI or ML in having prosthetic limbs help or assist in walking. And so we have to have some algorithms in place that might tell the robot, or the artificial limb, how to move to assist the walker, for instance, in the movement. Autonomous vehicles, we have a pretty large group here at Virginia Tech called the Virginia Tech Transportation Institute that is very interested in autonomous vehicles and doing autonomous vehicle research. So we have smart roads that basically can allow or can create environments, so rainy conditions or icy conditions or other things like that, and sort of simulate different road conditions and hazards. So there's a lot of research there. One of my colleagues does search and rescue research. So they're deploying drone swarms and having these drone swarms canvas a space to look for maybe an injured person or a lost person or something like that. So there's a lot of research in having, how do these drones move, cover space, and find the target of interest. One of our larger groups here is Jian-Bin Huan in our electrical and computer engineering group. In terms of core hours on our AI machines, this guy is kind of the one who uses the most. His goal is really to use visual data, so pictures, video, and understand and synthesize kind of our life. So kind of, create a virtual world, but do so with data. And so they're using machine learning to assist in labeling data. So we have lots of labeled data, but maybe we can create more either through deep learning and sort of artificially labeling, or sort of supervised learning techniques. So he kind of does both. Okay. So in terms of on-demand, again, this is kind of one of my passions. What is it? It's a plug-in free web experience to facilitate users' use of HPC systems with the goal of getting users onto our systems fast, and then through combination with something like XDMoD, facilitating their progression from new to more advanced user by basically looking at job performance. Okay, I'm gonna kind of leave it open there. Are there questions or thoughts?
Thanks, Bob, for the wonderful presentation and sharing the experiences on the power system there at VT, which we inaugurated, sometime back. Anyway, in person. That
Yeah.
was a past. Okay. So, audience, participants, any questions, and also the panelists, any questions for Bob? I also would like to welcome, Agya Das from University of Wisconsin Platteville, to be part of this webinar as a panelist.
Thanks, Ganesan. This is Argo.
Yeah, I Argo. So, any questions?
I think there is a question in the QA.
Yeah. So, I mean, these are great questions. I'm going to leave the risk one to maybe Ganesan, but the other one, how good is the Power software stack? It's extremely good. So what we see is that, out of the box, IBM has done all the hard work for us. So, my job as a computational scientist often will dive into software installs. And so I can spend a lot of time installing software and then worrying about optimization. And so IBM's done that work for us, which is super helpful. And so our users benefit from it. And then me as a computational scientist, I don't really have to work to make sure that it is optimized for power. It's already been done. So that's quite nice. In terms of how much, say, acceleration do you get from that versus an unoptimized, that's kind of a leading question, and it really depends upon the application. So in terms of a fold number, I don't have one for you, and it would be highly application dependent.
Thanks for addressing that question now, Bob. So related to RISC-V, that's another angle to it. Abhishek, we will discuss this offline. We do have some plan on that too.
So I have a question, Dr. Settlage. So it's not more on the technical side, but most on the strategic initiative side. Since you told about you organize hackathons, you offer some teaching tools on this Huckleberry cluster. So what I was wondering, I mean, do you offer it only for the VT student, or you are up for collaboration with other universities or outside students and faculty members also?
I mean, I would love collaboration, and there's nothing stopping people from joining us here. This fall we were gonna hope to do one, and I decided that this whole virtual world is too confusing for me, and so I canceled it this fall. But I'm hoping to do it again in the spring, and if that's something that you'd want to collaborate on and jointly host or something like that, love
sure. So yeah, I mean, actually, I am very much I am a strong supporter of this online education and everything. So I have developed my own online education platform that I have presented in the OpenPOWER Summit also. So I really would like to collaborate with different universities like Virginia Tech and everything. I mean, so that I can get access to these type of like innovative tools that you have told and innovative clusters. and can arrange all these things. I mean, so that the worldwide community can get some help. So if you are up for that, then we can possibly discuss offline regarding this topic.
Absolutely. And I'm one of the ones that's hopeful that the spring is a different world. So,
Exactly.
I'd love to talk more about doing that, as early as the spring, but if it's better for the fall, we could do it. I try to do kind of like one per semester.
Sure, I'm okay with the fall. I mean, that's okay. We can initiate the talking. Thanks.
Yeah. Yep.
Thank you, Agedas, for the question. And any more questions from the participants as well as participants? You can raise hands. If you want to ask a question, so that I can allow you to talk. Or you can also post it in chat window where Bob, will respond to you, over the chat window too. Okay. Yep. Thanks again, to Bob. Thanks a lot, for the wonderful presentation and for your time, Bob. Really appreciate it. And let's move on to the second one. The second presentation is going to be from Nikki, my colleague from OKFC IBM, and let me pronounce her full name. Nikki Anzivina, and she's going to be sharing the power systems academic experience.
Okay, hello everyone.
Academic, yeah. Nikki, please go ahead. Part of your presentation.
Okay, so hi everyone. I'm Nikki Anzivina, and speaking of ACC, I'm a Syracuse graduate. So I do follow the ACC in athletics, but my other degrees from other institutions are not from schools that had very good sports departments. So I stick to following Syracuse. So I wanted to talk to you about Power Systems Academic Initiative. And could you see my screen?
Yes, Nikki, please go ahead.
Okay. This is a shot of our website, www.ibmcom.com/university/power. When you click on that, this is the screen that you see. And when you get to the home screen, you could see this Learn More. If you click on the Learn More, it brings you out to a PowerPoint presentation, which I'll go through. But I wanted to explain a little about what Academic Initiative is first. IBM has an overall program for Academic Initiative that is an umbrella over on top of each brand. So there's an overall academic initiative, there's mainframe academic initiative, power academic initiative, quantum academic initiative, cognitive class, there's some storage academic initiative, and a whole host of hardware and software available under the academic initiative programs. So I manage the subset of that, which is power. Now I'm going to switch over to the PowerPoint presentation. So what we really do is provide educational materials, cloud access, and access to subject matter experts to colleges and universities who join the program. We've been in business for quite some time now, and we've grown slowly and steadily each year. The main thing we try to do is teach students about power through their professors, of course, so that when they graduate, we can provide market-ready power skills to our clients and help fill their hiring pipeline. Right now, we have 858 schools in 73 countries, so we're worldwide. And we teach, we educate, we provide educators with the materials, technology, different resources, application software. Then we try to help connect educators with their local power systems community to encourage collaboration. And then we try to facilitate matching up students with companies who need skills to help some of the kids get jobs. So right now, this is what we're looking like as far as geography. And as I had mentioned, these are some of the things that we provide at no charge to colleges and universities. Our program is 100% complimentary. So we have about 60 different courses.
Nikki, one question actually. We are just seeing only the first slide, the IBM Power Systems Academic Initiative. Are you?
Oh, wow. I am on the 5th or 6th slide.
Yeah, can you make the changes so that the audience can see your slides?
How do I do that?
See,
if you have multiple monitors, can you try just mirroring them?
Now I've even lost my Zoom window. Oh no. Gosh, I've lost my Zoom window.
It's in a different tab, probably in the same browser.
Yeah.
Oh,
Is
yeah.
that better?
Yeah, we got it. Yeah, thanks, Nikki.
Sure. Okay. So I'll go back a little bit. This described, our mission and the things that we do with our 858 schools. This shows the 73 countries that we're in, or geographic areas, and how we're distributed. This is the page I was on, indicating that on a complimentary basis, we provide courseware in the operating systems, Cognitive, Zend, Red Hat, and SUSE. And we have educational resources that we provide to schools. We have our job board, which posts internship, entry-level, and experienced professional jobs. And we have our academic cloud. My cloud is in Tucson, Arizona. I have approximately 60 assets in there, a combination of servers, storage, and peripherals. And my architect manages that cloud on a 24/7 basis. So we have full-time availability and help desk. And our cloud could be used for teaching classes, projects, or any non-commercial research that the college does not charge for. And it helps if it's open source too, so then we could have them share it and connect with other schools. Some of the skills taught in the program, this is what we try to focus on to make students more knowledgeable about power and marketable when they enter the workforce. So we go through operating system, the flexibility of a power box, experience with the entire stack. We have a whole bunch of Power 7s that we have separated from our production environment, where we can give students hands-on experience with bare metal. So we get them in through an HMC, and because they're not connected to our production network, they can experiment and play on the machine, and if it breaks, it's no big deal. Then we promote power hardware and architecture in the open source market. We teach utilities, various Power VM, SC, VC, the HMC, live partition mobility, and BIOS, among others. This is just a quick snapshot of what's in our cloud. Right now we have Power 7 Plus and Power 8s. We are getting 5 or 6 more Power 8s before the end of the year. Mostly, we stick with N-1 technology because we provide education on a complementary basis. We have to try to manage our budget. So we try to pick equipment that has depreciated some before we take it. And at any given time, approximately half of our schools are on the cloud doing either courses or projects. So out of the 858, we'll have between 400 and 500 on any given month or so using the cloud. We have a job board. Next year, our job board is going to undergo a major revision to be more user-friendly for both the job seekers and the job posters. I'm working now to get that set up for next year. Right now, it's a basic job board where clients can post jobs and students can register and post a resume and go out and look. But we're going to be enhancing this in 2021. Here again is a picture of the website. And if you look along the right-hand navigation in this slide, you can look at courses and resources for AIX, IBM I, Linux, our cloud curriculum, and cognitive. And then we also show participating schools all over the world. So this is just a snapshot of our curriculum at a glance. If you want to know more details, I can go back to the website and cycle through the tabs, or you can explore it on the website at your own pace. These are some of our PHP and Zend courses for IBM I, and some of our Red Hat classes that weren't captured in that little snapshot. Some of our SUSE classes. And the last page lists all the contact information. So our homepage, our job board, the overall description of Power Systems Academic Initiative, access where you can contact our architect and request being able to use our cloud. But our general email, which will direct you to anything you might need, is powerskills@us.ibm.com. I'm going to pop back over to my Zoom window.
Yeah, sure. Thanks, Nikki. This is a very, very detailed information about the academic initiative. I'm sure, there are like nearly, I would say, 30 plus university people, part of this call, and faculties, are there. I do see that, and also from the panelists also. So certainly, the job, post and all the stuff is very interesting, and certainly people would love to learn all these courses and look for job opportunities, and hopefully people do. We do know that the power has been for the enterprise for the last 30 years, and certainly there are a lot of job opportunities with these skills. Thank you for your presentation, and time for question and answers. Audience, participants and panelists, any questions for Nikki?
I have a question.
Yeah, please go ahead.
So you guys have the quantum computer, and it looks pretty awesome and all that. I'm wondering what software you have that might emulate that we might be able to install on our power cluster to really start to train our users on what quantum is about, and what it means to compute in sort of a quantum world.
Yeah, I can connect up with my counterpart in Quantum Academic Initiative and ask if they have anything publicly available to try to connect power and quantum.
Well, even if it's more of an emulator, that would be interesting.
Okay,
And
I will
then,
see what I can find and take a note, and I will get back to you.
yeah, and then if it is an emulator, there's some third party, not third party, there's some smaller providers that are kind of popping up that are putting emulators on FPGAs and, you know, touting this as the next best thing to a quantum. And so I'm wondering if maybe you guys have something similar on some of the FPGA cards that you offer.
I will definitely look into that and get back to you.
Yeah,
Thank you.
Bob, that's a very good question actually, and you know, I do have an answer for that too immediately, because I was part of you know, the quantum simulator project, you know, which was done by IBM Research some time ago. As Nikki said, you know, definitely, you know, she will get back to you with that, you know, on that. So there is a quantum computing simulator on Power. You know, developed by some of our IBM colleagues, you know, in Japan. So we will share it. Thank you, Bob, for the question. Very good. And
I just pasted my email in the chat. So
yeah.
after this presentation, if you think of other questions, feel free to reach out to me.
Yeah. Any other questions for Nikki? Maybe we have one more minute. Audience.
Nikki, I have a question actually. So you told about all these academic initiative, and I think our university is also a part of it. And some of the professors are using this also quite actively in our university. And so my question is it all like university specific, or can I register personally also to learn something, or for my personal initiatives also?
It is colleges and universities only.
Colleges and universities only? All right.
Yeah, and
okay.
some high schools. We do work with some high schools who have computer science departments.
Okay.
But yes, we provide these basically to students and professors.
Oh, that's great. So, I mean, you work in the high school domain also. That's good to know. Because
Yes.
we, in our university, actually, we have started having some kind of K-12 initiatives on data science perspective. So maybe we can talk offline regarding that.
Sure.
That's good to know. Thanks.
You're welcome.
Thank you, Agya, for the question. Thank you. And any audience, if you have any more questions, please, you know, go ahead and post it on the chat window or question and answer window. Nikki will be available to answer that too. Thanks, Nikki, for the presentation, detailed presentation about the academic initiative. Thank you.
Oh, yeah, thank you.
Yeah. And let's move on to the third presentation. It is actually going to be from Ajay Arasanipalai. I'm always, you know, challenged to pronounce the last name, even my name also. Sorry for that. Anyway, so Ajay is actually from UIUC, you know, the second year undergrad, and he's a very, very, I would say, like, you know, we know, the open power world knows him, you know, for last 3 years. He even presented, you know, when he was in his 12th grade, you know, he came to US and did a presentation in Open Power Summit in Las Vegas. And with that, you know, I'd like to invite Ajay to do this, you know, the presentation here. Ajay, go ahead, please.
Okay, thank you. So yeah, I'm Ajay, and I'm a student at the University of Illinois at Urbana-Champaign. And today I'm going to talk about attention mechanisms, which is this powerful new idea that's being used a lot in deep learning. And it's, you know, achieving state-of-the-art results in both NLP and computer vision. So to start off with, what exactly is an attention mechanism? So I believe that, fundamentally an attention mechanism is a way to route information. But what information? In deep neural networks, generally we have, models that take in some sort of input tensors and, spit out some output tensors. So really the information that's being routed here is those elements of the tensors. How do you capture meaningful information from your inputs and relate those to your outputs? Another thing that is usually cited when talking about attention is how they have the ability to capture global features. Typically convolutional neural networks, the way they work is by aggregating, simple local features, by looking at lines or patches of color, in the image, that kind of stuff. And, by building a hierarchical representation of all those low-level features, it, eventually develops a representation of what's actually going on in an image. Attention, however, looks at the entire image all at once. And this allows you to capture some interesting information. For example, say you have an image that has a dog and a cat both in it. Typically, convolutional neural network might struggle on the type of data. However, an attentional model understands the global context of the image. Now, another useful thing that happens as a function of using attention is you get better interpretability. And this is because what attention is actually computing is an attention weightage between different positions in your inputs and outputs. And these are values between 0 and 1, which are typically easy to visualize and can lead to some interesting results, such as this one over here. So this is the results from a model that was trained to perform image captioning, which is looking at an image and trying to write a description of it in natural language. So this problem itself isn't entirely new, right? Image captioning has existed for a while. We've been getting improving results, and so it's not entirely surprising that this works. But what's interesting over here is that since this model uses attention, you can point to a specific word in the output and see how that relates to the input using those attention weights. So, for example, in this sentence, a woman is throwing a frisbee in a park. If you highlight the word frisbee and try to look at the attention weights that correspond to that word, we can see that the model seems to be picking up that there's a frisbee in the image. And there are a few other examples over here. There's a dog, and it's able to find the dog. There's a stop sign, it's able to find the stop sign. But I mean, even these are somewhat understandable, right? These are the most important and noticeable parts of the image. So I guess it isn't entirely surprising that it's able to key in on those. However, look at this example. Over here, we've highlighted the word trees. And instead of focusing on the giraffe, which is by far the most important, it's the foreground of the image, and it's what's clearly visible. When you highlight trees, the model actually points its attention weights towards the trees and not on the giraffe. So this is more simpler, a direct example from natural language processing. So this over here is a visualization of a translation task from French to English. And what's going on over here is that you're seeing a matrix which visualizes the attention weights between the output and the input. And this is useful because English and French have different ways of writing sentences. For example, the adjective might come after the noun in French and the other way around in English. But what we're able to see is that the French equivalent of environment is pointing towards the English environment and not the exact position it is coming from. So we can see that attention is really learning some sort of interesting representation from the structure of the input. So how is attention actually implemented? Well, in practice, multi-head self-attention, which is proposed in the original transformer paper, is one of the most widespread approaches. I don't want to spend too much time on the details and implementation of this particular layer, but in short, what it does is for each position, it generates a query, a key, and a value. And all of these are vectors. So it takes the query vector and it tries to find the corresponding value by comparing the query with each key, forming a dot product, and then performing a softmax applying a softmax function over that to get a distribution over the possible values. So in this case, and this is just a simple analogy. This isn't actually how it's implemented. There are a few more details, but when the model is trying to resolve the word "it" and trying to figure out what exactly it is referring to, it assigns a high probability to robot, and this is like after it's trained. So the dot product between it and robot, like the key of robot, turned out to be high, so it assigned a higher probability to it, and it's able to pick out the value corresponding to that particular word, thereby resolving the word "it" to robot. So another thing that's I guess commonly confused is important to point out is the difference between self-attention and attention. So attention is when you have a mapping from your input to your output, and you want to see how the different values in the input relate to the output. So for example, when you're doing image classification, you want to create a weighting between each position in the input or each pixel in the input to the output, and sort of creating like a map of the importance, like how much is each region of the input relevant to the output. Self-attention, however, is a mapping sort of draws dependencies between the input and the next representation of the input. So in the transformer architecture, so this is specific to NLP, self-attention is applied inside the encoder part of the network. So this is the section that reads in an input sentence and builds a representation of what that sentence means. So self-attention over here, as it's building its representation, it looks at the entire sentence multiple times and tries to understand what that sentence actually means. So attention in NLP in the transformer architecture is used between the encoder and the decoder. So the encoder is the section that reads in text, builds a representation of it, and the decoder is a section that takes in that representation that the encoder built and tries to output something useful. Like for example, if you're doing sentiment analysis, it might output a sentiment class, or if you're trying to generate text like a language model, it would output words. So attention over here, not self-attention, is creates a weightage between different positions in the encoder to the current outputs that's being generated by the decoder. So in terms of actual numbers though, for each output that an attention layer generates, it computes n attention weights, where n is the number of positions in your input. So for example, if you're working with an image classification problem again, n here is the number of pixels in your image, and it's going to create n attention weights. Attention weights again are numbers between 0 and 1 that in some sense signify the importance. However, self-attention creates mappings between the input and itself. So each pixel would have an attention weight to every other pixel in the image. So if you have n pixels, then you're going to have n square attention weights, because you need to map every pixel to every other pixel. So that sounds nice and all, but how does this actually work out in practice? It seems like we're doing a lot just to get these interesting results, and you're actually right. So self-attention is very memory intensive, and unfortunately is not entirely practical for people who don't have enough GPU resources at the moment. So just to give you a sense of this, if you want to try applying self-attention to a single full HD image, that would be 1920 times 1080 pixels. That's the full HD resolution. And if you want to you do some sort of self-attention on this, then you need to create a map between each of those pixels to every other pixel. So that's 1920 times 1080 squared, which is a very large number. Another example of this is GPT-3. So this is a recent language model, created by OpenAI, and this has 175 billion parameters. GPT-3 is, based on the transformer architecture that uses a lot of this self-attention and attention computation. And so having 175 billion parameters, it requires 22 GPUs, not to train, but just to run inference. So to make a single prediction with GPT-2, like if you want to just do, a simple positive and negative movie review classification or something like that, you're going to need 22 GPUs just to, run the forward pass of the network. So it's not very computationally efficient at the moment. So a lot of solutions have been proposed recently. I'm just going to go over some of them in very briefly. So Reformer is a recent transformer-like architecture where instead of looking at each mapping every input to every other point in the input, you sort of cluster them and you create groups. The idea here is that, for example, if you're working with images and you see a dog and a cat in the same image, you'd likely want to compute the attention weights for all the pixels that are related to the dog region, and independently compute all the attention weights for the cat region. And then instead, an image has a lot of blank space, so there's a lot of stuff like the clouds, the background, the sky that you may not want to waste computation on just performing all these multiplications. So Reformer has this idea called local sensitivity hashing, which is essentially grouping grouping different points in the input into clusters or buckets, and performing self-attention within those individual buckets. So the short version is just a way to cut down on the computational complexity of self-attention. Another model that's been proposed recently is Longformer, and this is actually, computationally speaking, is more expensive than the baseline models they compare to. And it's portrayed a little differently in the paper. They make it seem like this is something that's meant to cut down cost and make it more practical to work with longer sequences. But actually, the way it works is, the typical transformer, so, it has a fixed length representation that it can take in. So this could be like a sentence composed of 512 words, and you can't pass in more than 512 words because that's how the model is built. And also, if you make this sequence length too long, then it's going to computationally explode, because like I said, it requires n square attention weights. So if you have 512, that's 512 square attention weights at each layer is what you're computing. So it's not practical to make this long enough to fit entire, let's say, documents of text. So what Longformer does is they implement a sliding window across the input. So they take the transformer that can take 512 tokens at a time, and they slide it across the entire document, a longer sample of text, and sort of do self-attention between each of those windows. So this isn't I guess in the same spirit as self-attention, because you're not getting that full global feature representation. But it's one technique to cut down on computational complexity. And there are a lot of other similar architectures that have been proposed. But the core that they're all getting to is that in deep learning, we want to see some sort of a layer, or some sort of a way to perform this attention mechanism that is getting the relationship between different points in the input, and collecting these global features without incurring such a high performance penalty, without incurring that n square cost. And so a lot of these models claim to have linear complexity. So that is, if you can keep growing the size of the input, and the amount of memory it consumes will grow in proportion to that. But yeah, this is still an active area of research, and it doesn't seem like we have a perfect solution yet. So still very much an open problem. How do you come up with a more efficient attention mechanism? So switching gears a bit, and I want to talk about a project that I've been working on in collaboration with a few people. So Diganta Mishra from Landscape, and Trike and Alamada from IIT. So triplet attention is another attention module, and here we're only is designed specifically to work with vision models and vision tasks. So we wanted to create a sort of module that performs this attention computation, generates the attention weights, that's efficient, that's not too memory intensive, that's fast, and at the same time gets good performance. So here's the basic idea. We take the input to our layer, the triplet attention layer, and we create 3 copies of it, hence the name triplet. And on each of those branches, we perform a few special operations. But before that, we perform these rotations. So we generate the 3 copies, and then we rotate one of them such that each of them have a different 0th dimension. So over here, the input shape might be the number of channels times by the height by the width. And over here, we rotate that to be the height by the channels by the width. And yeah, so for each of those 3 branches, once we perform the rotations, we do 2 operations. We first perform this thing called Z-pool, which I'll explain in a moment, followed by a regular convolution and apply a sigmoid. So what happens in the end is that we generate these 3 masks, and by passing it through a sigmoid, we squash the values between 0 and 1. So we generate these 3 sort of masks, all of different sizes, but we broadcast them to the size of the original input and average them all together to create a final attention mask. So this output of our layer, the attention mask, is going to be a tensor of size C by H by W. So it's the same size as the input, and it has values between 0 and 1. These values indicate the importance of those particular pixels, the corresponding pixels in the input tensor. So once you have the importance map, you perform an element-wise product of the input with the attention mask, and this sort of refines the input in such a way by incorporating the cross-dimensional interaction that we get by rotating these tensors and performing these operations to get that attention map. Applying the attention map, it refines it, makes the input tensor cleaner, and once you pass it on to the next layer, it hopefully gives you a better representation. So the Z-pool operation that we use over here is actually relatively straightforward. It takes an input that has size C by H by W, and it performs across the 0th dimension, hence the name Z-pool. Across the 0th dimension, it performs an average pooling and a max pooling, and it concatenate those results together. So this gives us another tensor of size 2 by H by W. And then we perform convolution on this, pass through a sigmoid to the broadcasting averaging. But in the end, what's important is that the result is we have a representation. We have a mask that tells you which parts of the input are important and which parts aren't. So all our entire layer is composed mostly of convolution and pooling, and the sigmoid. And these are all operations that have been extremely well optimized to run on NVIDIA GPUs. And they're really fast, and so overall we don't use any new special fancy operations. We work with what we have, and that's how we keep the computational complexity down. So here are some of our results. So firstly, we have the baseline ResNet 50 and ResNet 101 have these many parameters, these many flops, and they have a certain accuracy. But what I'd like you to notice is that the ResNet 101 achieves an error rate. This is on ImageNet, by the way. This is an image classification task trained on ImageNet. The ResNet 101, the baseline model, with 44 million parameters and 7.85 gigaflops, it achieves an error rate of 22.63. Our module, when applied to a ResNet 50, achieves better performance than that. So it has a lower error rate than the larger ResNet 101, at almost like half as many parameters and significantly fewer flops. So you get better performance at a good computational cost. And if you look at the difference in parameters between our ResNet 50 and the baseline, it's negligible. It's there weren't enough decimal places to show the difference in the number of parameters over here. We've also included comparisons with a bunch of other similar model-similar layers that implement a similar idea of some sort of global feature extraction pipeline, which gives you attention maps in some cases, and we've compared with some of those models over here. And yeah, in general, we seem to be performing extremely well. But of course, how do you validate whether an attention mechanism actually works? Well, you need to look at whether it actually picks up those global features or not. So to demonstrate that, we use this technique called GradCam, which essentially, given a trained neural network that takes in images and makes class predictions and image classifier, you can sort of go back through the image and look at the gradients and see what the network is actually looking at. So let's take this example over here. The baseline Resonate 50 looks at this image, focuses on the iPod, and says it's an iPod. And this is, in this case, an incorrect classification. Apparently, according to ImageNet, this is a tape recorder. Now, I understand that both these items are in this image, but according to ImageNet, this is a tape player. And our model, on the other hand, is able to correctly identify that this is a tape player, and it isn't giving too much weightage to the iPod, despite the fact that it's there and that an iPod is a valid class in ImageNet. We also compare with this other model called CBAM, which seems to be doing something similar to the original ResNet. Take a look at this example over here. This sort of, again, shows that it's able to correctly identify the features that are most important to making a prediction. Over here, the vanilla ResNet seems to just create this generalized circular region of focus around what seems to be the image over here, and it predicts it's a syringe, which seems reasonable given the shape. It turns out that this is actually a power drill, and our model is able to look at the global context, and we suspect that of course it's hard to say these things with certainty, but it seems like it's able to get the global context of the image to make the correct prediction. And again, the GradCam heat map over here is much tighter and centered around the actual object in consideration, whereas over here it's this general circular pattern that we're seeing. And we observe this pattern with a lot of other images as well. The vanilla ResNets just seem to be creating this general circular pattern, whereas ours correctly it expands when required, but it's also very specific and fine-grained when it needs to focus on something. So yeah, that's a quick insight into triplet attention, which is our work. If you're interested, you can check out our website. We have a preprint on archive, and the code is publicly available on GitHub. After this presentation, maybe I'll make this site public, and if anyone's interested, you can take a look at the presentation and check out these resources. Also, if you're interested in learning more about attention, I guess just want to read more on how it's applied in NLP in much more detail, you should check out my upcoming book published by O'Reilly. And this is going to have information about all the NLP architectures and how attention is actually applied. Okay. That's I guess that's it from me. Are there any questions that I can answer?
Thank you very much for the wonderful presentation. Do you want to share some of your experiences on Power 9, which you got access in University of Oregon system?
Oh, yes. So yeah, I forgot to mention, but
hello.
Hello. Yeah. So yeah.
Yeah, go ahead, please.
Yeah. So all this work, the triple attention was powered and run on the Power 9 cluster at the University of Oregon. So thank you, Mr. Ganeshan and Dr. Shende for giving me access to that. That really helped us run some of our larger experiments, especially the ResNet 101, and we were able to quickly iterate and get good results on that. So thank you very much for providing access to that.
Yeah, thank you, Ajay. Actually, I got disconnected and I just got back actually. So there is another question, from from our Q&A window. Can you go and take a look and answer that live?
Oh, sure. So the question is that the weights decide the attention between the encoder and decoder? If so, what type of weight initialization is performed in attention models? So good question. Actually, the steps that I described are mostly parameter free. So the attention weights, between the different positions in general, like whether it's self-attention or attention, the attention weights are not learned, and they're not free parameters. Basically, they're computed by the dot product between the query and the key. So you learn, I guess, the weights that map from the input to the queries and the keys, and then you just perform the dot product between the query and the key, and that gives you the attention weights.
Thank you, Ajay. Any more questions from the panelists and the audience? Panelists, Professor Ragia.
Hello.
Yeah, go ahead.
Hey, Ajay, it's a really great presentation. So, I mean, what type of, are you doing any type of undergraduate research for all these things, or I'm curious about all these things. So how are you using this Power9 system for your research and collaborations?
Mm-hmm. Yeah. This particular work is, like I said, it's a collaboration between a few of us. We got in touch online and decided to work on this project. And again, all the computation was done completely on Power9 systems. So we had access to, I guess, two main clusters. One was this machine called HAL at my university, and the other one was the Orpheus cluster at the University of Oregon. So those are the two main machines that we used. And yeah, we used NVIDIA V100 GPUs on those, which were connected to the Power9 CPU.
Okay, that's great.
Sure. Any other questions, team? Okay, I think somebody raised hand. Hold on. I'll allow Yogesh to talk. Yogesh, please go ahead. Yogesh? Yogesh, do you have a question? I saw you raise your hand. Looks like, I do not know, he has some technical difficulty or not sure.
Oh.
Maybe he can send a question to us. Actually, everyone knows, the ID to send a question, Ajay.
Sure, I'll drop my email ID in the chat.
Yeah. Oh, hold on. Yeah, no, he has a question on the window right now. Can we use this for MRI images?
Yeah, sure. I guess, in general, you can use it on any form of images you have. If you're talking about triplet attention in particular, yeah, so we designed it to, work with pretty much any convolutional neural network based architecture in general. So it's just like one module that you insert. You can insert it in pretty much anywhere in the network, and it should improve your performance. So yes, it should work on MRI images as well.
Okay, thank you, Ajay. Okay, any more questions before we close the session. Hold on, let me see. Yeah, I think, yeah, if you have any further questions for Ajay or the rest of the speakers, Bob or Nikki, please do send us a note. And we already communicated about the place where to send questions, and even the further collaboration with our the academia initiative. These are all the opportunities for you to really collaborate with the top tier institutes, and come out with this kind of wonderful presentation, like what Ajay did for the last 30 minutes. He really engaged everyone on his pay attention to attention solution on Power9 system. Ajay, thank you very much for your presentation again, and I'd like to thank the presenters, panelists, as well as the participants who actively participated in this webinar, and really appreciate your time and effort on this, and looking forward to meet you all on our next webinar. Thanks again, and I'm closing the webinar now. Thank you.
Yep.
Thanks, Ganathan.
Thanks for having me.
Thank you.